Okay, so it is a true pleasure to welcome Sylvain Lacroix from Jussieu, Université Sorbonne in Paris, and he will visit us for this week. And he's staying in Tamara's office, so if you want to discuss with him, and he will give a couple of lectures of introduction to ODE IM correspondence. And the next one will be on Wednesday at 4. Sorry for the confusion, but okay, there were some... okay, so please.
Great, thanks. Well, thanks for the introduction, and well, thanks for the opportunity to talk here. It's my first time in CISA and Trieste, so it's a pleasure to be here. And indeed, so today what I would like to give is then some first introduction to the ODE IM correspondence. Is it fine if I write here for the camera? Or?
Yes, both. Everything is fine.
Yeah, great. Okay. So yeah, this will be then the first lecture on this ODE IM correspondence. And so, well, as the name suggests, this is some kind of duality between two seemingly unrelated sides, where the IM side here stands for integrable models. Integrable models, and more precisely, this will be integrable field theories, and even more precisely, integrable conformal field theories in 2 dimensions. So this will be CFT2 type of models. And in particular, this will not be integrable model with a finite number of degrees of freedom, so that will typically mean having an infinite number of symmetries of conserved charges, and we'll be interested in the spectrum of this infinite number of conserved charges. So that's one side, and the other side are ODEs, so ordinary differential equations, of in fact a specific type, which are Schrödinger type ODEs. So something, say, of this form here. Controlled by some potential, and what we'll see is that some properties of this ODE, like spectral determinants and quantum periods, will encode information about the integrable model itself. And so the plan of my lecture will be, in fact, to follow exactly these 2 steps. I will start by talking about the integrable model side and try to define what we're talking about here, what is the integrability that we want to study, and then I'll go on to the ODE. And for this first lecture, I'll keep things very simple by looking at just the simplest example of this ODE IM correspondence, which is also the first one that was found historically for what I call minimal models. And this was initially done by Dorian Tateo and then Bajanov, Lukyanov, Zavorotchikov. And let me then start with the first part, which is then about integrable CFT. So, just for the setup, I need to say a few words about CFTs. So I will have a 2D CFT on the cylinder here, which means I have a time coordinate t here and a spatial coordinate x, which I'll take to be then periodic. And in particular, what will be important for me is the existence of a stress energy tensor, which is a field of my theory, and more precisely, the stress energy tensor has 2 components, the left moving part and the right moving part for a 2D CFT. And here I'll focus on the left moving part, so it's a function of x plus t. It is quite often written t, but I would use t for something else, so I use the letter u instead. And this is then a field depending only on x plus t, and I can write it here as a Fourier series by decomposing it then in in exponential minus in x plus t with some Fourier modes Ln, and these are the Virasoro modes, which satisfy the standard commutation relation of Virasoro, which looks like this. Let me write it in a moment. So these modes will satisfy the commutation relation of the Berazor algebra, which is this infinite dimensional algebra here, where the modes Lm with an n close in L plus n, and then there is this central, what we call the central extension here, which depends on the central charge. C, which here I think just have being any real number. So this is the standard algebra of conformal transformation, and they appear in any conformal field theory. So it's kind of a universal algebra. The only part which is model dependent is this central charge here, which then depends on the choice of the specific model. And in fact, to really get this algebra, I need to make a slight change here, which is either minus C over 24, which is some kind of finite size correction in the stress energy tensor, because we're working on the cylinder and not on the sphere, some kind of Casimir energy type. So that's the standard setup for, say, 2D CFT. And in particular, I can translate this commutation relation of the modes in terms of the commutation relation for the field U itself, which looks like this.
Minus sign between central charge, is it type or is it your convention?
So this should be such that then if I want positive, if I want unitary representation, I take positive C.
So it is opposite. So for minimal models it will be negative.
C will be smaller than 1 then for minimal models.
And it should be plus.
Then it should be. Yes, sorry, I think I added with the M here, so yeah, sorry.
It's not this. No, see, the positive C, negative, they have different story, of course. Okay, it's minus. No, I think now it's correct, but yes.
It won't matter so much for what I'm saying.
I don't think people use this formula really.
Yeah. And I guess it will change the convention of what is the raising operator and the lowering operator, but okay. So if I go back then to my field itself, if I write a commutator, then this part of the commutator essentially translates to to a derivative of the Dirac distribution in x minus y here. And then the central extension term translates to something which is not proportional to the triple derivative of x minus y. And we'll use this kind of algebra later. And the last thing I need to say about the CFT before I go to the integrability is talk a bit about the Hilbert space. So in the cases I look, the Hilbert space will be built in terms of Verma modules of the Berazor algebra, which means, so this is something which is labeled by some number delta, which is the conformal dimension, which is the real parameter at that point. And that means I have a highest weight state delta, on which L0 just acts as a number, so it measures this conformal dimension delta, and then I'm saying that the positive modes here, Ln for n strictly positive, should be essentially raising operator, so they should kill my highest weight. And then the rest of the delta is spanned by vectors of the following form. So now what I'm saying is that now the negative modes, I interpret them as lowering operator, and so to create all the states in my Verma module, I just act with products of lowering operators with some 10 mode, arbitrary modes here. And that allows me then to construct all my Verma module in this way. Okay, so that was just the setup about CFTs, and now in there I can start talking about the actual integrability by introducing what I'll call the KBV charges. these will, I'll denote them IP n, and stars to p will be an integer double, and these will be operators of my CFT, which have the main property is that these commute one with another, and so these will be integrals of motion, they will be concept operators, that's the I, and they all commute one another, so that will be an infinite number of commuting conserved operators, and so that will be then what really captures the integrability of this theory. And the way these are defined is as local charges of my CFT, so they will be essentially integral over the spatial variable of some things, and then the first one is very simply just the integral of the stress energy tensor itself, right, which is then nothing but the left moving Hamiltonian of the theory, right, by taking the stress energy, integral of the stress energy tensor, and this of course should be part of my concept operators, right? And now I can translate this in terms of Fourier modes. If I just do this integral here, I'm essentially capturing the zero modes. So this is just L0 minus C over 24. Now what really in integrability is the presence of an infinite tower of higher kind of hidden concept operators. And for instance, the second one here will be built now by taking composite field in terms of U. So here I'll take U squared. And then I need to normal order it. I'll explain what I mean by normal ordering. So now we start doing products of fields here. And well, finally, if we take a product of two fields like that, of U with itself, if I forget about this part, what this would look like is some sum with an L0 squared, and then a sum over n of L minus n Ln. So this would be just doing this Fourier product where the mode n will be paired with the mode minus n. But now I need to be careful that this is an infinite sum, so that might not be well defined. And in particular, I see that if I have n going into the very negative number, I'll get more and more creation operators here, and so it will create more and more fields, so this will not be well defined. So the way I treat this is I normal order in the sense that I put here positive n, and I choose to put all the positive nodes on the right, which mean now they're raising operators and they will eventually truncate because of this property. And now this is well defined. And so this would be the normal ordering on the sphere, but now because I'm working on a cylinder, there are additional terms which here will just follow. The details do not really matter, it's just to be complete here that you can write them down. And they are purely expressed in terms of this C number. And then you can go on and compute all these power of charges, and just for completeness, let me show what the next one looked like just in terms of the field. So this would start with a u x to the cube, and then you would add a term which now involves also derivative of u. So I will take du now squared, and I need to add this with a very specific number in front, which is c plus 2 over 12 dx. And you can realize that essentially you need exactly this type of term for the things to commute with I2. You need exactly to choose this here. And then you will go on and we will start having more and more complicated densities that essentially will start with ux to the power of p, and then correction involving derivatives. And these are chosen such that they all commute. And just to mention how we get this commutation, the way we currently do it is we need what I call the generalized Leibniz rule, which is some formula that tells me how to take the commutator of a normal product with another field. And this looks like as follows. So this here would be the standard Leibniz rule, meaning that I can decompose my commutator here, I can expand it on the product. But in fact, this is not true anymore because I'm not doing a naive product, I'm doing a normal ordered product, so I need to correct this Leibniz rule. And in fact, there is a formula, so there are some corrections here. There's a very explicit formula for them. I won't write it because it's a bit technical. If you're curious, ask me later on. But the main thing I want to explain is that if I know all the commutators of A, B, C here, there's an explicit formula on how to do these commutators here, which means that starting from my fundamental commutator here of the stress energy tensor, I can compute the commutator of all of these densities. And essentially, I want to arrange that here when I commute, I get total derivative with respect to x and y of the density, so that when I take the integrals, I get something vanishes. And this essentially fixes uniquely all this tower of charges that commute up to just an overall scale. And that's my integral structure. So these are the local KdV charges of the integral structure. What's happening quite often in integrability is that in addition there will be non-local charges. They will play also a role, but in what I'll say, but I won't go as far in their definition here, just to say they're non-local in the sense that they're now, instead of being a single integral, they're a nested integral of this form of some operator, let me call it OP. Some nested integrals of some form with some operators here. And these are still the property that they commute one with another, and they also commute with the local KdV charges. And so these local charges and non-local charges together, they form what we call the KdV integrable structure, which is the thing we want to study here on the IX side. So in fact, a natural question at that point.
Since this is KdV, it means that U satisfies KdV equation?
Yeah, so the relation with KdV, so essentially now that we have all of these infinite tower of commuting operators, I can think of each of them as defining some time evolution. So I take the commutator HP with HP and if, well, maybe with I, and say that this is my time evolution.
IP or no?
IHP, yes, so TP. This is a TP. So I get one time for each of my operator, right? Defined by the commutation with HP, right? And now the claim is that if I...
You mean IP or HP?
What is HP?
Sorry, IP.
IP.
Sorry,
Okay.
Sorry, I was thinking Hamiltonian and then I got confused. Sorry, IP. And now in particular, so the first one will essentially be trivial because this is just my standard Lorentz Hamiltonian, which here acts by the words. But now the claim is if I take I2 and I look at the action on U, this will be a quantum version of KdV.
No.
You can show starting from there that in the end the equation you get is the quantum KdV. Okay. Other questions?
Yeah, do you have a trial formula for Q1, Q2? I mean, these no local charges that you were defining.
So here I almost said nothing about them except that they're not local in the sense that they're nested integral. One way to think about them is that these OP here will be built in terms of vertex operators. So I will do a free field realization of my theory, and then I will put here some exponential of that free field in some way, and then take nested integrals of these stuff.
Okay, you make a kind of spinning charge.
Some type of spinning charges type object, yeah. So these are Fatih style integrals.
But there is not a definition from the concept of a primary field or something like that.
I mean, these are rather complicated.
Okay.
I mean,
Sorry.
yeah.
And the Q suggests that there are box operators in some sense.
No, they won't be master. Wrong choice of notation, it seems. Other questions?
Sorry.
Yeah.
And all Q's commute with all I's. Yes.
Yeah, the Q's commute with each other and they commute with I. Yeah, sorry, it should be IQ, sorry. Okay. So. Now the main type of question we want to answer once we have this kind of integrable structure is we want to take these operators. So in principle, for instance, here I could always write them in terms of VR0 mode, and I can make them act on my Verma modules, right? And I want to look at the action of this operator in the Verma module. And if I start with the simplest one, so the I1 on d delta, and if I look at the action of I1 on my state here delta n that I define here, well, essentially you can convince yourself of the following. So in the end, this will be an eigenvector of this operator. If I had I1, which was just essentially my L0, and if it was acting purely on the highest weight, I would just get a delta. So here I would get a delta and then a shift by C over 24. But for this to be true, I would have to take my L0 and make it commute with all of these lowering operators. And for that, I would need to use the VR0 algebra. And if I do this, I can convince myself that essentially every time I commute with L minus n, I will shift to the eigenvalue by plus n. So here I will get then a shift by all these mode numbers n1 plus n2, right? So now the statement is that I1 as an operator of my Verma module is very easy to diagonalize. All of these are eigenstates with these eigenvalues. And in particular, I see that this gives me then the energy spectrum of my CFT. And I see that this energy spectrum is quite degenerate, because for a given choice of this eigenvalue, I get a lot of states that are the same eigenvalue. Essentially, the number is the number of partitions of these integers here. So this is something that grows quite big. And now this is when it's interesting to now get the integrability coming up, because now I have these additional operators that all commute with the I1. And so in particular, they will stabilize these eigenspaces. But in general, they won't have these delta n as eigenvectors. They will start mixing these vectors one with another. So I'll get like, on each of these eigenspaces, I'll get a finite size matrix, but mixing everything. And so in particular, the spectral problem of diagonalizing all these IP and QP will be well defined. It will be in the end just linear algebra, but it will be quite complicated because of course the dimension of these spaces, it grows quite fast. And so that's the main question that in the end we want to ask is, well, what's the spectrum of IP and QP on d delta? And what we will in the end see is that this spectrum will be encoded in some particular object related to the audience. Okay. And so to answer that question, in fact, it will be useful to to collect all of these operators into one unique object. So to define essentially some generating function for these operators. So I will have some generating function which I'll call Tj lambda. Lambda here is an auxiliary complex variable which I'll call the spectral parameter. And essentially it will serve as a formal variable to get all my charges expanded in the generating function. And well, I won't go into all the details at all of how this is defined, but the idea is we'll have an object m lambda that lives in a tensor product of two things. So one is a quantum group for the affine algebra SL2 hat, and then tensor the algebra of operators of my CFT. Right, so on that side here I have operators of my CFT, so for instance things of the VR0 modes or something like that. And then tensor with some object in an abstract algebra, which is a certain quantum group, which I won't go into the details here. And then what I do is I take this and I take the trace over the 2j plus 1 dimensional representation of UQSL2 hat here, where j is then the spin of the representation, so it's a half integer. So for every j half integer, I get a corresponding representation of this, and I can take the trace, and now I get something which is purely an operator in the CFT. Right?
So,
Yeah.
so which representation? I mean, for a final SL2, there are many encode.
So here essentially I'll take evaluation representation in the loop parameter, and that will become my lambda.
So
So
your
the lambda
parameter depends on lambda.
The origin of lambda essentially is the loop parameter here. And then on the finite side, I essentially take a 2j plus 1 finite dimensional representation. Right? So I guess maybe more formally here I should think of m as being this, and then the lambda is part of this loop parameter here. And then I take the evaluation representation. Right. And now the main statement is this m, it satisfies some nice commutation relation, which in the end are just a consequence of what we call the Young-Baxter equation. So this is like standard integrability lore, but it's not really the topic I want to get in today. But the main thing is that the integrability technique tells us that Tj lambda commutes with Tj prime mu for all value of the spectral parameter lambda mu and all value of the spins j and j prime. Yes.
Sorry, but what is definition? Okay, m belongs to this tensor product, but what explicit m? Right.
So I mean, here I said I don't want to spend too much time on how m is defined. This is actually that's the whole story. It could take a whole lecture to define it as well. Essentially, the idea is the following. So you start with the universal R matrix of UQ of the Borel part of this quantum group. You have another universal R matrix, and then you realize that objects, which are essentially screening charges of your CFT, satisfy the relation of this quantum affine algebra. So you get a representation of this affine algebra on the CFT. And then because you started with an R matrix that was satisfying Young-Baxter, then this M satisfy a RMM relation, which in the end tells you that these commute.
And then you present how it is connected with.
Yes, the next step is to say how to relate it to the Q and I's. So in particular, I see that all of this stuff produce for me commuting operators, and they produce commuting operators for all value of lambda and mu. And so in particular, these are good generating functions for commuting operators. And for instance, if I take the T lambda in the fundamental representation, so 1/2 here, this will just be the generating function for the QPs, right? So if I do a power series expansion in lambda, essentially what I will get here will be the QP. Yes.
Sorry, maybe you said, but so one more thing. So you're saying that the Young-Baxter is satisfied by M, correct?
So more precisely, Young-Baxter is satisfied by the R matrix, and then because M is obtained as some kind of representation of the R matrix, then it's satisfied what we sometimes call the RTC relation.
Yes. So M is an alpha of T. Is it correct?
Yeah.
Or
Yeah.
and this is an
And
alpha.
this is then the transfer.
Yeah,
so
this
this would be the monotony matrix. This would be the transfer matrix in the.
So this is similar to beta or what is that?
Yeah.
Okay.
Like bit transfers.
Yeah. This is quantum inverse scattering methods. But now the main difference, instead of doing this for a spin chain like we would most of them do, the quantum part is really a field theory. It's a CFT. And this is the work of Bajanov, Lukyanov, and Zamolodchikov. To realize that you get essentially a representation of this quantum group on the CFT, and that allows you to use all the integrability technique to produce commuting operators in the CFT. But here I didn't want this to be like a pure integrability stuff. I want to come to the ODE. So this, trust me, there's some algebra it works. Essentially, is the message. So you get then the QP, you extract them naturally from the T1/2, and just to say, if you look at the higher ones, so for higher spins, you also get a power series expansion. but it turns out it doesn't contain new data in some sense. It's just, you extract exactly the same operators QP from them, right? Just in other ways, so we get non-trivial combinations of these QP. So it seems like maybe there's no additional information here, but that will in fact still tell us something, because that will give us a structure, and in particular we then get what is called fusion relations from there, and it will be useful to also have then these higher spin transfer matrices, the higher spin generating function.
But the fact that we don't have new information is like, usually if you take tensor product of two-dimensional representations, you can obtain all that.
Exactly. And that will be the fusion relations. Yeah. I'll come to that a little later on. But in fact, we'll get some relation between the T's, and that will be something that will be able to map to this ODE side, in fact.
Yes. And then this isn't different parts that operator exists, we just take.
So these are really T operators.
Yeah, T, but
Q operators.
we can find we'll define box operator using this, just taking not finely dimensional, but
yeah, we'll take a pre-fundamental representation here in terms of Q oscillators, and then you would get the Q operators. But I'll focus just on the T operators. Okay.
And how is this related to E? Is it?
How it's related to the to what? Sorry.
To E.
I was thinking, yeah. This is what I'm saying now. So indeed, that was exactly the right questions. I said these are generating functions for the Q i's. Then is it also related generating function for the I? And the answer is yes. And essentially, what happens is you now need to do, instead of a small lambda expansion, you need to do a large lambda expansion. You do the expansion around infinity. But here, a lot of non-trivial things are happening, which is, in particular, that you'll get an inessential singularity at infinity, although this was entire as a function of lambda in a complex plane, and you get a more complicated behavior at infinity. And in particular, then you'll get an exponential type divergence when you look at large lambda. So we'll look rather at the logarithm of, say, t1/2 lambda. And this will have a behavior of this sort. So we'll get a dominant term which is divergent as lambda to the power alpha, where alpha is this combination of C. Yeah. So another non-trivial thing that happens is when you do the expansion around lambda infinity, in fact you get an expansion not in powers of lambda itself, but of a non-rational, like in general a non-integer power of lambda, which is lambda to this specific power. So that's the dominant divergent term. And then you get corrections to this. Where you extract essentially the IP. So you get now still an expansion in lambda to the alpha, but now with 1 minus 2p, so negative powers of this lambda alpha. So these are now smaller corrections. And you get some number AP, which is just a C number that we can extract. And then there's an explicit expression, but I won't give it to be technical. And then you extract the KdV local charges here. That's the expectation from the BLs. And here, in fact, this is not a converging expansion. It turns out to be only asymptotic, so in principle you would have to resum it to really get something converging. But if we just think at least formally lambda to extract the coefficient, then we see that it's a generating function for our objects. Okay. So now, was there a question?
So, alpha, this coefficient alpha can be complex.
So depending on the values of the central charge, it could be complex. So what I'll do later on, in fact this is where I'll go now, I'll get some C which are, it turns out, is smaller than 1. So in that case, I won't get any problem, this will be a real thing, but in general, yeah. Okay, so now I'll actually specialize a bit all this construction by looking at some specific minimal models m to m plus 3. So these are models that depend on some number n, which is just a positive integer. And they correspond to a specific choice of central charge, which I write here. So the details do not really matter, it's just for concreteness. So I get a specific choice of rational C here, rational central charge in terms of some number n. You can see that in fact this integral will be even smaller than 1 and even smaller than 0. This will be a negative central charge, so this will be a non-unitary model in general, but that won't be too much of a problem for me. And it turns out that in that case there's a bunch of simplification that appears in the Virasoro algebra. So you get some quotient, some null vectors that you can quotient, and in particular you also get only a finite number of representations of Verma module which are that you need to consider, and these representation they are labeled by some choice of the conformal dimension delta, which again I write for concreteness. 1, 2, n plus 3, and this depends on the number k, which is also an integer now going from 0 to n. And so in particular I get a finite number of representations that appear in my Hilbert space with this specific choice of delta. And what will be possibly interesting for us is to look at what I'll call delta ground state, which is the delta for 0. That is the, you can check that for k equals 0, this is where this number is the smallest. So in fact it's negative, smallest. So that means this will be in the end the ground state of the theory. That will be where the energy eigenvalue will be the smallest here. Right? And so by making this choice, it turns out I will get some interesting things about T.
In terms of cut stable, this is delta 0 is what? Somewhere in the middle?
Sorry?
In terms of cut stable.
Yeah. So these are, I mean, this is exactly the CAC table, right? So because I have 2 here, essentially it means that my CAC table, the R and S, the R is always 1, and then the S essentially is
right? Yes, and the cut table will have the n plus 1 representation like it here, but in cut table the first one usually is a vacuum, so it should have some ground dimension 0. And your convention is like k equal to m.
So here, k equal, so it's kind of the opposite. It's taken in the other direction.
So delta 0 somehow in the middle of this cut table, if I understand correctly.
Yes, I think, indeed. Because you have this thing that decreases with k, this will increase. I think to really get the maximum, where this thing is maximal, you need to go to this k here. Alright, so now I want to discuss is what is called the T-system, and in particular that will be one of the important things to map to the ODEs. So now, as I said, the TJs that we have, they in fact all contain the same information, they contain the same all the same Qs, which means that there should be some functional relations between them. And these functional relations, they are what are called fusion relations, and they look as follows. So I get these relations, so these they come from what you were mentioning earlier, that when I had this representation of the quantum group, essentially if I take tensor product, I'll create other representation, and by taking tensor product of the fundamental, in the end I can reconstruct all the others, which is why I will not get new information in these higher spins, but still it means they organize in some way, which are now functionally dependent one from another, and this is encoded in this T relation here, where the Q that appears is exactly the quantum parameter of my quantum group here, right? And so this integral, I didn't say, but the Q here in general it would be related to the central charge in some way. And this so far would in fact exist for any value of C. This is not for the minimal models only, that can be done for all the values of C. But when I take the minimal model, some nice things happen. So the first thing is that in that case, the value of Q becomes quite simple, and it turns out it becomes a root of unity. So it's a root of unity of order 2n plus 3, right? So we get some kind of cyclic property here for Q. And moreover, we get some additional functional relation between our T, which is the following, so Tn plus 1/2 minus j is equal to Tj lambda. And in particular, it means that if I look at Tn plus 1/2 lambda, this is the same as T0 lambda. And T0 lambda is just in the trivial representation, the trace in the trivial representation, so that's just the identity. And so now in particular what we see is that for these specific choice of minimal models, there's essentially kind of a truncation, and we get only a finite number of T's that satisfy this functional relation with some kind of boundary, trivial boundary condition, right? And so now instead of having functional, like infinite number of functional relations, we get a closed system of functional relations. In that case, it starts putting some constraints on the T's themselves. Essentially, that means some particular relation between the Q's that are true only for these choice of minimal models. And this is the type of functional relation that we'll recover from the ODE side. Okay. So this goes into the
verification. So when Q is a root of unity, then I mean depends. So what is quantum group is the delicate question. So for some definitions we have more than just this. We have another finite dimensional representations.
You have a whole complicated theory of the representation. This is not the type of things I plan to discuss, and I must say I'm not even sure exactly how it interacts with what I'm saying right now. But there are all these crystallographic representations and so on. But I'm not sure exactly how this would relate to my discussion right now. Okay.
I don't know, usually people start to complain about this other representation when they start to talk about logarithmic theories.
What's the reason?
When they start to talk about logarithmic theories. You know, like for triplet or singlet theories, when they start to look at linguistics, they always start to compare representations. So maybe if you consider minimal model, we don't see this.
Yeah, because these are purely rational CFTs, right? They're not.
If you extend it by some additional fields,
maybe you didn't get logarithmic stuff. I must say I'm not sure here. Okay. Okay, so I'm essentially coming to the end of this integrability part. Just to say the type of things I focus on today will be what I'll call the T functions. So these are write Tj lambda with a small t, and these will be the eigenvalue of big T, so the operator on the ground state of the theory. So this might seem like a rather trivial object, but it turns out already finding the value, the eigenvalues of all these operators on this ground state is already a complicated enough question, and I'll focus only on the ODIM for this ground state. Good. So last thing I say for the integrability part is that we can also define what are called y functions. So these are defined in some way in terms of the t function. So it's a specific combination of the t function, and the main thing is that these now, instead of satisfying the t system, they satisfy another type of functional relation, which is called the y system. I won't write it, but there's a formula for it. And what's particularly interesting is that this, in fact, you can show in the end that this can be mapped to what is called the TBA, the thermodynamic Bethantax, which is some nonlinear integral equations for y. And for this, you need to also some information about the analytics of y, so some kind of asymptotics and so on. And particularly this TBA are quite useful if you want to solve the theory, for instance, numerically. And from there you can extract then the values of these y's on specific states, like the ground states, using these nonlinear integral equations like TBA of TBA style. Okay, so to now summarize my integrability part and go to the ODE. So essentially now I have here part integrable models, and then later on I'll do the ODE part here, and I want to essentially complete these two columns and give some kind of dictionary between the two parts. So the type of things we do.
Why is, I mean, as you write there, it seems like a definition of why? Or
It's a definition of y, yes.
Okay.
Yeah. I just say I take these specific combinations of the t.
And then you have relations that they satisfy because they t satisfy.
Yeah, exactly. So there's a relation between the y system and t system, but this is practical because these are the ones which inherit here in the TBA.
Okay, that you will explain the TBA now. At some point. Okay.
In the TBA I won't go into too much detail, but this will also come from the ODEs in some way. This is just to mention that there are also these objects. So here the type of information we have on the integral model side. So what plays an important role is the spectral parameter lambda, right? And it will be mapped to something on the ODE side. Then maybe one of the fundamental objects is the t function, right? Which is essentially the eigenvalue of this t operator on some specific states. These satisfy some functional relation with other t system. And in particular, if you want to extract the local charges from there, so the KDB charges, you need to do an expansion which is at large lambda. And finally, there are the y functions which satisfy some TBA-like equation. And essentially, all of these ideas will get their equivalent on the ODE side, and this is what I want to explain now. And now I'll come to my second part. Which is about ODEs. So, I'll consider a very specific ODE. Which is essentially a Schrödinger type ODE with some very simple polynomial potential, where here the n is the n of my minimal model, so we see that it's just a monomial of certain degree, which is some kind of anharmonic oscillator, right? If this was 2, then I would have a harmonic oscillator, but now I get some anharmonic oscillator, right? And in particular, I look at the corresponding eigenvalue problem with some eigenvalue lambda. So if I want to study these ODEs, I can do, for instance, a large lambda, large W expansion. And this, I can realize that this gives me the following type of behavior. So I get a power law behavior in W, some normalization which does not really matter. And most importantly, I get some exponential type behavior. Some normalization. So this you can just check by looking at the large W behavior of psi in this ODE, right? And basically what you see is that these solutions, they will be, they can be either dominant or subdominant. So this exponent, because of this exponential with a plus minus, depending on where I am, so I'll think of W as a complex variable, and depending on the argument of W, this can either essentially decrease very fast or increase very fast at infinity. And then I'll call that either dominant or subdominant solutions. And so in particular, then we introduce psi 0 W lambda as being the subdominant solution when W goes to plus infinity, right? So on the real axis with positive W, in that case I take the minus sign here essentially, and that gives me the subdominant solution. And now the little trick I'll do is I'll introduce psi k of W lambda, defined as follows. This is called the semantic trick, semantic rotation. So I take Q is my root of unity, which was defined over there, right? Same root of unity as before. And essentially I do rotation in the complex plane by this root of unity. And what will happen, so I can do a drawing here. So let's say here I do the drawing for n equal 1. What will happen is I'll get solutions which are dominant in different regimes. I don't know if I've covered chalks, no, maybe not.
We can search for it, I don't know.
I think it's fine, it's not that much. So essentially the idea is I get different sectors like this. So for n equal 1 I get 3 different sectors, which I'll call S0, S1, S2, and then the S3 essentially goes back to S0 because of cyclicity, and essentially in order of psi k, this will be the subdominant solution in the sector Sk, which is defined as the W such that the argument of W is close to 2 pi k over 2n plus 3 with an opening of I over 2n plus 3. So these are what I call the Stokes sector. And essentially, so if I look for instance here, psi 0 on the real line is subdominant. And then when I get to that point here, essentially this is where this exponential factor now, what's in exponential becomes purely imaginary. And so that will become then oscillatory on this line, and then when I shift to S1, now this becomes dominant instead, right? So psi 0 is only dominant here, subdominant here, and then dominant here, and then essentially by doing this rotation by Q here, I now have a new solution, which is now subdominant in S1 instead, right? And I get then all of these things. And the reason that works is you can check that if you do this rescaling of W and the rescaling of lambda, you essentially get a power of Q in the overall ODE here, and because Q is a root of unity in the end, it vanishes. So if psi 0 is a solution, then if psi k is a solution as well.
You take any integer k?
Sorry?
You take any integer k?
Yeah, k essentially here will be also, here will be an integer.
So W is in the universal cover, not in C. The sector.
Yeah.
It's not, W is not in C, but in the universal cover of C star.
You mean by Z? By Z?
Because these sectors can have any several sectors, like an helix.
But here I think I really think of them on the complex plane.
Yeah, if you take k equal to 0, 1, and 2.
Yeah, yeah, exactly, yes.
Not in the integer.
Yeah, here I identify essentially S3 with S0 here, right? OSM. Okay, and so why this would be interesting? Well, for that I need to introduce maybe I should not. I'll introduce Bonskians. So I'll call WKL of lambda, I'll define it as being psi k dw psi L minus psi L dw psi k. And it's a very standard fact about ODEs, about linear ODEs, that if psi k and psi are solution, then this specific combination is independent of W. Okay, it's a constant. And in the present case, then it will depend only on lambda, the eigenvalue. Right? And these satisfy a number of properties, so W of k, k plus 1, it turns out this is 1. If I take the Wronskian between two consecutive sectors, it turns out to be always 1. We can check it because of the asymptotic formula that we have. And moreover, the way we interpret this is, well, if I take psi 0 and psi 1, they're dominant and subdominant in the same region, it means that there should be a basis of solution. So I can take any psi k and decompose it into psi 0 and psi 1, right? Because I have only a two-dimensional basis of solution. And essentially the way I decompose it is with this Wronskian. So I get that psi, this is psi k0 minus psi k1 psi 1. So this Wronskian can put it as kind of a way of expanding any solution in terms of psi 0 and 1, in terms of others in other sectors, essentially. And now I can get to the first main claim of the ODE correspondence, which is that Tj lambda, which is thing I think just erased. So this was the eigenvalue of my T operator on the ground state. This is nothing but the Wronskian between the sector 0 and the sector 2j plus 1, evaluated at lambda but slightly rotated, so q to the power 2j minus 1. So my eigenvalue generators on my integrable model side turns out to coincide with the Wronskian between different Stokes sectors on the ODE side. So now I'm essentially starting to fill in my part here, where now I have some Schrödinger ODE of this form here, so some Schrödinger type ODE. Then I see that the spectral parameter on the ion side, it turns out to be then lambda here, which is the eigenvalue, the energy eigenvalue of the Schrödinger equation. Right? And of course, here the eigenvalue is very different notion of eigenvalue. Yeah.
So, sorry, I cannot understand. What is this statement, the WK plus 1 equal 1? It is a condition or an identity?
This is an identity. So this, if you start with this, I essentially fix completely what is subdominant by putting some specific normalization here. This 1 over square root of 2i could be in principle arbitrary. I chose this normalization, and in this normalization it's chosen such that two consecutive subdominant solutions are of Wronskian 1 on consecutive sectors. You can essentially use this asymptotic formula to compute the Wronskian specifically, and then you'll find here that it's 1 for k plus 1.
The Wronskian is constant, and you can put this constant in some asymptotic.
Yeah, exactly. So because the Wronskian does not depend on W, I can evaluate it very far, and then I can use this asymptotic formula, and the normalization has been chosen exactly so that it's 1.
This is just our choice of normalization.
Yeah, it's a choice of normalization. So here then the spectral parameter is mapped to the energy eigenvalue. And of course here the notion of eigenvalue is for Schrödinger operator, it's not the eigenvalue of the integrable commuting operators. Then as we said, the T functions get mapped to Wronskians. Right? And here I won't really go into the detail of that, but these we can also interpret them as spectral determinants. Because the Wronskian essentially, we get Wronskian between subdominant solution. If this Wronskian vanishes for a special value of lambda, it means that essentially we have some specific line somewhere here where between these two we get some solutions which are subdominant on both sides, and then it will get L2 normalizable, and then it means we'll get a solution of the actual Schrödinger operator with L2 condition. So these then are spectral determinants in that sense as well. They vanish when we are really on the spectrum, when lambda is in the spectrum. And then, in fact, one of the, so here I just say that this is one of the main claims of ODE. one of the good hints that this is true is, well, remember that these T's, they were satisfying this T system, right, this functional relation. It turns out that Wronskian also satisfies some functional relations, which are called Klucker relations. So this Klucker relation, in fact, is very simple. It's just we take some quadratic combinations of Wronskian in 4 functions, and just we do some kind of cyclic permutations of these, and this, just because of kind of the skew symmetric definition here, they will vanish identically. It's very simple to write it down. But if you take the Klucker relation for these W's with good choices of what are my functions, it turns out to be exactly mapped to the T system that we had in the IN side. And so that's maybe one of the first very important hints that we get a relation between these two sides. We recover the same type of functional relations. Okay, so then we recover the T systems.
Lost it.
I guess I can go on a little bit in terms of time, right? Yeah. Okay. So then next on my list here would be, I want to understand what happens with the local charge expansion, which recall was the expansion when lambda was going to infinity. And now, well, the idea is that to study the lambda to infinity limit of this ODE, it will be useful to do a small change of parameterization. So I'll change from W to some Z, which is related to it just by scaling. Right? And if I do this, essentially, I can convince myself that it's such that now I get also a lambda in front of my power here, which means I can think of them being together. I also get some power of lambda coming from there, and I can put everything in front of the derivative, so I can rewrite this in the following form. Second of z plus z2n plus 1 minus 1 times z equals 0. So I essentially put this at the same normalization and put everything in front of this double derivative by introducing a new parameter h bar, which is related to lambda more in the following formula. So that's just a small change of variable. And now we're back to kind of the standard Schrödinger form, right, where I have the Planck constants. And in particular, what I see is that here large lambda will correspond to small h bar, right? And this, I will study it using the exact WKD expansion. So this will be for small h bar, which means large lambda. And the idea of WKD is the following. So I will search the solution of my psi for my ODE as the following ansatz. So I write my solution in terms of a normal function s, where here I take some integral, I get some square roots. And the idea is if I take this and put this back inside of my equation, my Schrödinger equation, I'll get some type of Riccati equation, which I'll be able to solve at least formally by doing a power series expansion in h bar. And so I get an asymptotic expansion for this s here. It starts with the 1 over h bar, and what I have here is z to the 2n plus 1 minus 1. So essentially the square root of this. And then I have some high order term, SPLP of z, and 1 to p minus 1. So here I won't go into the detail, but the idea is that these specific ansatz here turn out to be compatible with my Schrödinger equation in the end by doing a full expansion in h bar, and then I get some recursion relation for these functions s tilde p of z. And well, this is not converging, and again, this is asymptotic, and then you learn the whole Borel summation, resurgence story, and so on, but at least here I'll think of it just as a formal power series. And one thing that we
So when
realized.
you say exact, you are referring to the resummation, exact WKB.
So exact here is because, so it's not WKB in a sense of large shed, it's because WKB can also mean that. So this, in some sense, some people might also think of it as being some type of WKB. But now I really want to think that I do some infinite power series in h bar. And then, in principle, indeed, to get the full solution as a really true converging analytical solution, I would need to do a Borel reservation in h bar. Yeah.
And it's exactly before the last line. No?
I mean, this is then something. And now, well, what I see is that when I want to do the large lambda expansion, I need to do small h bar, and what I see is that I eventually get odd powers in h bar when I do this expansion. And now the kind of magic observation is that this specific power of lambda turns out to be exactly lambda to the power minus alpha, where this alpha was this weird parameter I had when I was doing the large lambda expansion on the IM side, right? It was this with square root of 25 minus c and so on. If you take the specific choice of c, which is the minimal model, then this depends on n, and it becomes exactly this thing. And so now we see another hint for this ODE correspondence, which is that the WKB expansion on the ODE side turned out to involve exactly the same power of lambda that what was appearing on the IM side in this local charge expansion. And we see in particular then that in this table, the local charge expansion should map to the WKB expansion. Right? So that's kind of another indication that maybe we're doing something right here. And a particular interesting observation related to this is if I look at the y functions. So recall the y function, there were specific combinations of the t's. Right? It turns out that in that case, I can express them as follows. So they will be exponential of integral of this S here, which we sometimes call the WKB momentum, on some contour gamma j. I won't go into the whole detail about this contour, but essentially it's the contour in the cover where this square root is defined here, right? And what this is something also very standard from the theory of ODE, which is called the Borel symbol, which is also another word for it is the exponential of the quantum period. So there's another mapping here, so I won't really explain where this comes from, but this essentially you start, the y is it depends on the t's, and you get essentially some specific combination of the t from which you can reform some integral over a closed contour using these kind of this type of expression in c's.
Sorry, what is gamma g?
So gamma j is some contour on the cover where this square root is defined here. I won't explain exactly what it looks like. It's a bit technical, but essentially it's some contour that will go around some of the zeros of this function here, and that will essentially cross a branch cut once and then cross another branch cut somewhere else, so that in the end it's a closed contour on the covering. And so in particular then I get another thing here, which is that the y function then maps to Borel's symbol, or in other words, quantum theories. And in particular, recall that if I have t functions or y functions and I do large lambda expansion, I'm supposed to get back the local IMs from there, right? And essentially what will happen in the end is that the eigenvalue of my local IM IP will be encoded in the integral over some contours of my function S twiddle pz. So recall that essentially in the coefficient of h bar to the power 2p minus 1, this was the coefficient of lambda minus alpha 2p minus 1, and this is where we extracted IP. And so in the end, the eigenvalue of IP up to some factors will be essentially encoded into this type of objects, right? And in fact, this will be kind of the starting point for my next lecture. I want to develop a bit more this idea about local charges, WKB expansions, and try to explain a bit more where this could come from in some way. So this is a small advertisement for Wednesday. And maybe one of the few things I can say now is, well, so we say y functions don't have to be Gauss symbol. It turns out that in the theory of ODEs, Gauss symbol, they also satisfy some nice relations. So to really get the true y symbol, I will need to resum this asymptotic series, which I can do by Borel summation. But in general, we will have some poles in the Borel plane. So we will have some ambiguities essentially in doing this, and we'll have the whole theory of resurgence that tells us essentially some discontinuities in the h-bar plane when we do this Borel resummation. And that in the end will translate into what are called DDP formula. So these are the Dillinger-Delader-Pham equation, which gives the discontinuity formula in resurgence. It doesn't matter so much. But what's interesting about it is that you can translate this into some Riemann-Hilbert problem. Some Riemann-Hilbert problem whose solution turned out to be nonlinear integral equations, which are exactly the TVA that you would get for the y functions. So you can also interpret the TVA on the integrable model side as essentially being some Riemann type, Riemann-Hilbert type problems on the ODE side for these Gauss symbols, which is something which is also well known from the theory of resurgence of ODEs. Yeah. All right. Okay, so I think on the ODIM side, this is most of what I wanted to say. So just maybe to say a few more words. This was for a very specific case, which was the ground state eigenvalue, right? We can look at other choice of Berman modules, so other choice of deltas. For this, we need to change a bit the ODE, and then essentially the whole story works similarly. And we can also do excited state, in the sense that we can go deeper in the Berman modules, not only consider the highest weight state, but having excited state. And that is also something that we can do at the level of the ODE. Essentially what we need to do, we need to add additional terms in the ODEs that seems to have some punctures, and asking that these punctures, in fact, there are no monodromies around, that in some sense they were a bit artificial, and that will give us some kind of better equations for these excited states. And this, I will also talk a bit about this in the next lecture.
But what do you mean with other deltas, not the minimal model ones?
So okay, maybe I can be slightly more explicit. So let me write it down here. So if I want to do excited states in V delta, I need to do two things. So I get my ODE, so the start of my ODE is the same. So I'm still looking at the minimal model at that point, right? So I still have the W2n plus 1. Now I add one term, which is essentially angular momentum term. So L delta plus 1 over W squared here. This essentially is how I would go from the delta ground state to the arbitrary delta, and there's a formula, a relation between the L and the delta. I won't give it, but it's explicit relation. And in fact, there's one first interesting comment here, which is, recall that for the minimal model, we have some specific discrete choice of the delta, a finite number of delta. It turns out there are exactly the choice of L such that this has no monodromy around 0. Right, so it's kind of natural also from the ODE side. The specific choice of delta that appear in the IN side, in the minimal model, they also are nice on the ODE side. And so that would be the ODE for the highest weight. And now if I want to do the excited state, I need to add -2 W squared sum k log plus 3 minus alpha t. Rewrite it in there. So this will be my complete ODE where I add these weird terms. So some double derivative of some log. So again, I could write this as some rational functions, some W with some new poles depending on these alpha k, right? And essentially, these alpha k, they're fixed by requiring that the ODE has no monodromy around this alpha k, it's called. And so that gives a system of algebraic equations on the alpha k which are fixed. And essentially, once we have this, it means that we're going to be on a, this will correspond to an eigenstate on the IM side. And then the whole story essentially follows. We can still construct these type of objects here, and that will encode the eigenvalues of the INs of all my my integrable model. So a few remarks on this. Then is this is for the minimal model. Then so this is for a very specific choice of CFT essentially, right? There are other examples of the ODIM. So you could do, for instance, instead of Mira0, you could do W algebras. In that case, instead of having just the stress energy tensor, you would get also higher spin currents essentially in the algebra. And you can also construct some integrable structure in there, and they will be typically encoded in higher order ODEs. So instead of second order Schrödinger ODE, you will get now higher order ODEs. There's other cases, for instance, there's also, you can do Zumino-Witten theories, you can have a whole lot of different choices. And in fact, this will also be a little bit what I'll discuss in the next lecture. So one of the points is that historically, guessing the right ODE was always a little bit of an art. There was a lot of guesswork involved in this somehow, to try to get the right functional relations and so on. But what I want to explain on Wednesday is some more recent things, which is based on Langland's duality, which gives a kind of a more systematic way of constructing local some integrable models and mapping them to ODEs. And in particular here, one of the points that we can observe is that the Z or the W, so the ODE variable, it seems to play absolutely no role on the integrable model side. This was purely auxiliary. This was a new variable. It had nothing to do with the spatial variable of the CFT and so on. And in what I explained on Wednesday, in fact, we will see that in this formulation called alpha inguinal models, this Z here will play some role in the construction of the integrable model itself. And so that starts to explain a bit more the origin of this relation. And maybe a final comment is that I could add a third column here, which is about n equal to gauge theories in 4 dimension, where a lot of these quantities are also mapped there. So in particular, the ODE will be the quantum Sylvain curve. And then, for instance, the y functions, so the Boros symbol, they will be related to Darboux coordinates on hyperkähler moduli and so on the Hitchin moduli space. But, well, that could be another lecture in itself, so probably I could stop now.
Are there more questions?
So far, this correspondence is just at the level of experiment. So we don't understand why.
No, so yeah, at that point, this is really more like observation than the same type of object appears in true. So, I mean, if you arrive deep in, like far enough to really, for instance, at the Riemann-Hilbert problem that maps to the TDA that kind of characterizes completely your functions, and then you can essentially see it as a proof that the two things give the same object, but this is very indirect. Like in the end, you have to go through other type of equations to map the two things. And this is also precisely one of the things that will motivate what I'll say on Wednesday, which is to try to have something a bit more systematic on how to build the ODE from the choice of the integrable model. And that will be guided by some long stack duality.
Suppose you said that you start with an ODE and you want to guess what is the integral model on the other side.
That's a very good question. So if you have, so on Wednesday I'll give you a rather large class of ODEs for which there will be an integrable model. And if you turn out to land in this class, then you can of course reverse engineering. Whether all ODEs can in the end be mapped to this kind of objects is not obvious at the moment. So, well, so far at that point, I think the answer to your question is we don't really know. But I would claim that maybe what I'll say on Wednesday is at the moment the best shot we have at trying to reverse and engineer the IM from the ODE. And maybe just one point is, one thing you could try is to start with the ODE, try to write down a Riemann-Hilbert problem, translate it to a TBA, and then try to map the TBA to some S matrices and so on. In which case you might kind of recreate at least a scattering matrix of the integrable model, which would almost serve as a definition in terms of factorized scattering theory, but that's a long shot, like it's a long road to that.
So just a quick question. So alpha k fixed by from monogamy, and moreover this should happen for all lambdas simultaneously, is it correct?
Yeah, this is for all lambdas. And this gives a rather strong condition. In the end, that gives it some coupled algebraic equation on the alpha k, which essentially maps to some kind of beta ansatz, algebraic beta ansatz on the IM side in some sense. And this I will do also some example on Wednesday, where we will have some additional punctures where asking for that there is no monodromy will be mapped to some beta ansatz type equation on the integrable model side.
Probably a stupid question, but this system seems like a consistency equation. So I was asking wondering if they can be bootstrapped in this sense, right? So you can get some information from that equation.
So if you start just from the T-system,
yeah, like.
So the T-system, it will give you some constraints, say on the eigenvalues of the Q operator, of these IP and QP operators, but I don't think you can completely solve the theory just from them. I think the Y systems, in that sense, they're slightly stronger because in the end, together with some information about the analytics of asymptotics, you can essentially use them to completely solve the theory in terms of TBA. But I'm not sure from the T system purely. It depends exactly what you want to reconstruct, but
Not like ODE spectrum.
really you mean on this just purely as a pure 2D CFT question? Well, I'll be honest and say I don't know. In some sense, I think this integrability story, this is already getting. And this is not so much about the CFT. I think the CFT here is more the setup in which we work and in which we will define our integrable model. But if you care about purely CFT questions like what are my operators, what are the Hilbert space or Riemann module that appear, I don't think you really need to talk about all these integrable structures. This is more like the right setup to define these integrable models, but I don't think I don't mean integrity for these type of models really tells you more than the standard theory of CFT, like just the Gerasimov representation would tell you here essentially.
More questions, comment?
What about massive integrable fields?
Good. Yes, so you have a way of doing massive deformation. So for instance, you take the minimal model and you add a phi 1,3 operator. This will trigger an RG flow and give a massive theory in one of the directions. And in that case, you can essentially, you have a deformation of all this, which sometimes goes in the name of PDEIM, where essentially you will now get something which is not only ODEs in Z, but you will get some type of PDEs in both Z and Z bar, and you will be able to extract also some, to be also able to extract some of the information about the integral model from there. And in the n equal 2 gauge theory side, this is essentially turning on the twistor parameter in the Gauss-Mornitz story, but this is a whole realm in itself. Yeah.
More questions? Comments? Okay, so if not, we thank Sylvain again. And then the next lecture will be on Wednesday at 4 in the room Dubrovnik. I will send an announcement.
So that's the reason why everybody who speaks in a seminar has the Now I understand.